Gradient descent is the engine of modern AI, but what if the very concept of minimizing a loss function is holding us back from solving complex, discrete problems? This paper, Learning Without Loss, proposes abandoning the error landscape entirely in favor of a geometric approach derived from physics. Standard neural network training relies on flowing downhill via gradient descent, but this fails when the landscape is jagged or full of false bottoms. The researchers argue that minimizing error is a fundamentally limited way to teach machines, especially when dealing with discontinuous functions that break standard derivatives. Instead of optimizing a loss function, the authors propose we conceptualize learning as finding the intersection of geometric sets. To solve this, they adopt the relaxed reflect-reflect algorithm, or RRR, a method originally used in phase retrieval physics. While standard approaches struggle to slide down error surfaces, RRR treats the problem as a set of constraints and bounces variables between them until a valid intersection is found. This method effectively splits the network state into two distinct constraint sets, one for linear operations and one for activation functions. By projecting the system state onto set A and then reflecting it towards set B, the algorithm iteratively converges on a configuration that satisfies both the math and the neuron logic simultaneously. The results of this geometric approach are striking. On difficult non-negative matrix factorization tasks where standard methods failed 99% of the time, RRR achieved a 100% success rate. It also successfully trained networks using discontinuous step functions and demonstrated a unique ability to automatically exempt eccentric or mislabeled data during training. This creates a fundamental alternative to back-propagation, enabling neural networks to handle hard, discrete logic problems that were previously out of reach. By trading loss surfaces for geometric intersections, this paper offers a robust path toward handling discrete structures in deep learning. For more insights into alternative learning paradigms, visit emergentmind.com to learn more.